Hi, and welcome to another episode of LongCovid on the Short, where today we're going to be talking about microclots, an area of LongCovid research with a significant amount of evidence that has been replicated in multiple papers and by different labs. So what exactly are microclots? First, let's take a look at their full name. Fibrin, amyloid, microclots. Why do they have this name? Microclots are abnormal formations of a protein in your blood called fibrinogen, hence the fibrin. Normally, fibrinogen takes part in hemostasis, helps prevent bleeding, and supports coagulation. Unfortunately, in certain situations, fibrinogen can clump, that is, change its shape into an amyloid shape that is much more resistant to degradation due to its physical properties. Finally, microclots, because even though they have a different composition from normal blood clots, they do behave in a similar manner, just at a smaller scale. So think smaller and rather affecting the small and very small blood vessels rather than the big ones. In late 2020, Professor Regia Pretorius, who studied clotting pathologies in autoimmune conditions, published a small report showing that during the acute phase of COVID and independently of severity, COVID patients had a much higher presence of fibrin amyloid microclots as compared to patients with diabetes type 2, who are known to have microclots in their system, or compared to healthy individuals. Upon hearing of persistent symptoms post-COVID infection, Professor Regia Pretorius and her collaborator Doug Kell decided to investigate the occurrence of microclots in patients with LongCovid. For this, they tested the blood of 11 LongCovid patients together with the blood of 13 patients with acute COVID, 10 with diabetes type 2, and 13 healthy individuals, which revealed that microclots were present in patients with LongCovid, just like in the patients with acute COVID, and again, significantly more raised than in the blood of people with type 2 diabetes or in healthy individuals. You can see here on the images on the left what these microclots look like in the different groups. Now I want you to understand how resistant these microclots are. So for example, every time you go to get your blood tested, your blood actually needs to go through a process called digestion before it can actually be tested. So they did the same thing here. What they found was that these microclots were so resistant that actually the blood of LongCovid patients would form a pellet at the bottom of the tube because these microclots were so hard to digest. So they actually had to do a second step in order to be able to digest that pellet. Once they did manage to dissolve the clots, they actually found that many coagulation and inflammation components were actually trapped inside the microclots, sometimes in concentrations up to 10 times what is normally found in acute COVID patients and in healthy individuals. Now, these results were further replicated in another paper, this time with 80 LongCovid patients. And furthermore, even though it hasn't been published yet, I know that these results have been replicated by 2 labs in the UK, and the United States, there has at least been 1 lab who's been trained to identify microclots. One thing that I really want to stress out though, and that is very rare, very important for clinical trials and scientific findings, is that every single one of these patients had microclots. Every single LongCovid patient. Now, we know what microclots are, and we know that they're present in LongCovid. But what do they do? Well, first, I hope that you understand that I cannot give you a 100% correct answer because the science is still developing. What we know is that they should definitely not be there. Professor Doug Kell has explained some of the potential mechanisms of these microclots and how they can block your small blood vessels and prevent your cells from receiving oxygen and much needed nutrients. This is actually the most similar part to normal blood clots. In normal blood clots, when a vessel is blocked, it leads to ischemia of the tissue that is after the clotting area. And for example, if this happens in the heart, that tissue stops receiving oxygen and nutrients and can die, leading to a heart attack. Microclots potentially rather do it in smaller areas, or they lead to a starvation of oxygen and nutrients over an extended period of time. Our cells use oxygen to produce energy in the most efficient way. However, if oxygen is not available, the cells switch to a different way of producing energy, which is much less efficient and is much more wasteful. Now, let's say that the microclots have reduced or blocked the blood flow to a certain region, the cells are going to switch to this mode of energy production and are going to produce a lot of waste. This waste remains localized while the blood flow is not coming. However, when the blood flow comes back, either because the area was unclogged or because a new tiny vessel was formed, all of this waste is released back into you, potentially making you feel much worse depending on the extent of this process throughout your body or throughout a certain region. Professor Kell explains how this could be a potential mechanism behind post-exertional symptom exacerbation that I mentioned in my previous video. Now, we've looked at the direct research in microclots, but I actually want to present you two secondary evidences for microclots in different papers. If you look at Buenosenso and colleagues 2020, these clinicians find evidence that in a 14-year-old girl with long COVID that was reporting breathlessness, although her lungs had no structural damage, an exam called SPECT showed deficits in perfusions that the authors attributed to microthrombi in her lungs. Now, this is just another word for very tiny clots. Now, another much larger study with 34 long COVID patients reporting breathlessness has similar findings. This time, using magnetic resonance imaging and a gas that behaves like oxygen but can be seen in an MRI, researchers find that in many parts of the lungs of these patients, the gas is not being properly absorbed. Again, no structural damage is seen in these patients' lungs, and the researchers hypothesized that something very small has to be blocking the very tiny blood vessels of the lungs. Now, with direct and indirect evidence, we must also wonder, why are these microclots here? It has been shown that a part of the coronavirus, the spike protein, can cause fibrinogen to assume this amyloid shape that is resistant to degradation. This phenomenon is not seen with spike proteins of other viruses, and for the record, was in fact stronger with the Alpha and Delta variants as compared to the Omicron. The big question now is, why do the microclots persist in people with long COVID? And for this, I don't have a good answer to give you, as research is still developing these answers. It could be due to some form of viral persistence, but it could also be that the initial acute infection set off a chain reaction of microclots and damage to the endothelium that now is not really being stopped. But more research is needed to answer this question, and it could also be that microclots are just a downstream event of a more essential process to long COVID. Alright, so that's most of the research I wanted to share with you regarding microclots. I do want to finish with some notes on blood analysis, potential treatments, and other resources. It's now more typical to test D-dimers after a COVID infection. This is something that is only produced by clots that are actively being degraded by your system. But its results should not be misinterpreted for microclots, because they are much more complicated to degrade. So a negative D-dimer result shouldn't tell anything about the presence of microclots, okay? Now, what I'm about to say is by no means medical advice, but Professor Kell and others have alluded to the fact that because these microclots are of a different composition, fibrinolytics like nattokinase and serrapeptase might degrade microclots much better because they are actually targeting fibrinogen. If you want to be more informed about what nattokinase and serrapeptase do, I absolutely recommend that you check the Twitter page of LongCovid Pharma Doctor. She's extremely thorough in her analysis of how this potentially works, how someone can take this, what to expect, what you need to be careful with. So I definitely recommend checking these resources. So finally, as promised, I want you to have some resources that you can go to continue the research on your own. So of course you have the links that I always put of my references in the video description, but you can also check these ones where you can find interviews with Regia Pretorius and Professor Doug Kell. It's mostly done by Gaz Mediger and the LongCovid sessions, who have done an amazing job bringing information directly from the experts to us. So that's it for today. I hope that you found this video informative. Next week, we're going to be talking about vascular and endothelial dysfunction. Stick around if you find these informative. As always, stay safe. And if you're on this boat, I hope that your recovery is steady, if not quick. Bye.